Well, hello. I'm Matthew Brenneman, and I wanted to take you through this last proof, which is essentially showing that the space of functions that are Riemann integrable on a closed interval are closed under multiplication. Okay. So I'm going to step you through the proof, and then I'll make some comments afterwards. So we start off the proof by supposing that we have some finite interval AB, and we have two functions, f and g, that are Riemann integrable on it. And all Riemann integrable functions on closed bounded intervals have to be themselves bounded. This is actually not something that your book proved. Your book actually says that boundedness has to be part of the definition of an integrable function. But it is true, and I don't think your professor wants you to show this, is that on a closed bounded interval, you have to be bounded to be integrable. So in other words, integrable implies that you have to be bounded. Okay. So we can suppose that both f and g are bounded, therefore their absolute values are bounded, and we can find some common upper bound on f and g both, which we're going to call m. So m is a positive real number such that f of x is less than or equal to m, and the absolute value of g of x is less than or equal to m for every x in AB. Okay? We can assume that. That's not a big deal. So the way we usually prove integrability is we can use the criterion that for every epsilon, there has to be some partition such that the upper sum minus the lower sum on that partition has to be less than epsilon. If we can show that for every epsilon there exists such a partition such that the upper Riemann sum minus the lower Riemann sum is less than epsilon, that is sufficient to prove a function's integrable. So we're going to start off and let epsilon be given positive number, and we're going to define a new epsilon, which is epsilon divided by 2 times m, and m is this bound. Okay, how would you know to do that? You wouldn't. We know how to do it because we've basically done the proof. Your professor wouldn't even probably do this step. He would go through the very end and get this result and then say, okay, now let's let epsilon be less than epsilon over 2m. Okay, but we can do it up here. So since f is integrable, for this epsilon, there is some partition such that the upper, and you can call this upper Darboux or upper Riemann sum, minus the lower sum on that partition is less than epsilon prime. And because g is integrable, there is some other partition, probably won't be the same, p sub g, such that the upper sum minus the lower sum of g on this partition b sub g is less than epsilon prime. And what I'm going to do, and this is kind of one place you have to be a little careful, is I'm going to look at the common refinement of p sub f and p sub g. I'm going to call that p prime. So basically I'm adding all of the points of those partitions, right, and getting a common partition. We call that a refinement of p sub f and p sub g. Okay? So you're just adding all of the endpoints of both of these partitions, and you're getting a finer partition. That's why we call a refinement. And so p prime has some finite number of intervals, and we're just going to call this number of intervals in p prime n. Okay, and I can call this subinterval, 1, subinterval 2, on up to the nth subinterval. Okay? Now, for every subinterval, I'm gonna arbitrarily choose 2 points in that subinterval, alpha j and beta j. They're arbitrary points, okay? And I want to look at this sum. So if you want to, you can think of alpha j as being points of a certain set of points from these partitions, and beta j being a different set of points in these partitions. So let me just illustrate kind of briefly what I'm doing here. So this is the first subinterval, right? And I'm just going to randomly choose an alpha 1 and a beta 1. I'm not going to put any sort of restrictions on them. In fact, I don't want to. So let's just suppose this is alpha 1 And let's suppose this is beta 1. Then for the second interval, maybe, beta 1 is here, and maybe alpha 1's the actual endpoint here, right? And I can keep doing this, okay? I'm just going to choose 2 arbitrary points in each subinterval, okay? And I'm going to look at this quantity, and you'll see why in a second. So I'm going to look at f beta j, times g beta j minus f alpha j times g alpha j. And then, of course, I'm going to take the absolute value and multiply it by the length of the subinterval. Okay? Now, very often when we do proofs involving limits in products, we do this little trick. These are called epsilon over 2 proofs. Well, notice what I'm doing here is I'm adding and subtracting this term. Okay? And there's a reason why I'm doing that, because I want to split this right-hand side up. Okay. Up to this point, this is actually in equality. I'm writing less than or equal to, but technically, if we want to be really careful, although it's not, actually I should really write equals. At this point, I haven't done anything. Okay. But what I'm doing is I'm adding and subtracting this term, and then I'm breaking this up. Now the inequality holds by the triangle inequality, right? This is an absolute value here, okay? And now what I'm doing is I'm splitting this up, and I'm writing this like this. And I'm factoring out. You notice that when I group these two terms together, I can factor out an absolute value of g beta j, right? And when I collect these two together, okay, I can factor out a common value. There's a common factor that comes out of the absolute value of f alpha sub j, right? Okay? Now each of these are bounded. So in going from here to here, I'm using this information on the bound. I'm saying each of these is less than or equal to m, and so I can pull this m out, and notice these guys go away, and the m comes out in front. All right? Now notice something, that this difference is always less than the sup of f minus the inf of f on that subinterval, right? These are just 2 arbitrary differences. In fact, this is the absolute value of 2 arbitrary differences, but they're always less than the sup minus the inf. Okay? And so now I can basically replace these. I can hold the inequality holds, and I can put these values in here. Okay? But notice what this is. This is the upper sum of f. Okay? And this is, this is the upper minus the lower sum of f. Okay? If I collect up all these supremums, this gives me the upper sum of f on that partition, right? And if I collect up all these guys, I have a finite sum, so I can break this up. Let me just illustrate, just to be careful, okay? And let me look at this, at just this quantity right here, okay? I'm going to split it up, all right? And I'm going to write it like this. And I'm going to be a little lazy here. I'm just going to write I sub j, okay, for the jth interval. I'm going to take this and I'm going to split. I have a finite sum. I can do this, right? Okay. Notice this is, and I need delta x j here also, right? Okay. This is the upper Darboux, or the upper Riemann sum, right? What is this? Well, this is the sum where I'm taking the supremum of each interval times the length of that interval, right? And this is the lower Darboux or Riemann sum, depending on how your instructor says this, right? So these things break up. Well, I know. I cold-bloodedly set this up so that this was less than epsilon prime, right? I specifically chose this partition so that it was less than epsilon prime. Okay? So each of these become less than epsilon prime. And epsilon prime is defined as epsilon over 2m. So I get that this arbitrary quantity here is less than epsilon. Now, notice something. Notice that this holds for any points, and this is the key part of this proof. This holds for any alpha j and beta j in this subinterval. So I get to choose, and I'm going to choose this to be the maximum. Beta j is going to be the point that maximizes this. So beta j is chosen here. So I'm going to choose beta j such that f of beta j, b of beta j is greater than or equal to f of x, g of x for every x in the jth subinterval. Okay, I get to pick. So I can pick this to be the value that maximizes that product, right? I can also pick the alpha j so that they minimize that. Okay? And that's the trick, the fact that I get to pick. So this is the supremum of f of the product fg on this subinterval, right? And this is the infimum. Okay? Well, if that's the case, if I choose these to be the supremum on each subinterval and this to be the infimum, I'm getting this, right? And so now this becomes the upper Darboux sum of the product on that partition minus the lower Darboux sum on that partition. And this becomes less than epsilon. Since it's true for every 2 points I choose, I'm going to choose this to make this the maximum, this to make this the minimum. That'll make that the upper sum, that'll make that the lower sum, and I get my result. And so what have I shown? I've shown for every epsilon, there exists a partition of AB, that's P prime here, such that the upper Darboux sum minus the lower Darboux sum on that partition is less than epsilon, and that proves that the product FG is integrable on AB. Now, one word of caution. We used a result here that your teacher may or may not allow you to use. We use the fact that if we have a partition P sub F and P sub G, and I know that the upper minus the lower sums, in other words, if I know that this upper sum minus the lower sum is less than epsilon, and this upper sum and lower sum is less than epsilon, the refinement can never give an upper minus lower sum that's greater than epsilon. Okay? So the upper sum for a refinement is always less than the upper sum of the partition it comes from. So here's what we're trying to say here. I'm just going to illustrate this like this. This is less than, okay? And the lower sums are greater. So if I actually kind of plot this, okay? This is P prime. This is going to be the lower sum for P prime. This is the upper sum for P prime. Okay. This is the upper sum for P and the lower sum for P. Okay. So the lower sums of a refinement increase, the upper sums decrease. So this difference can never be more than this difference. Okay. So refinements reduce the difference in lower and upper sums. That's a fact you need. And I don't know if your instructor will let you just suppose that. I don't think it's in the book. But this is pretty common knowledge, and I think your book uses it. But you might want to be a little careful about that. Okay, I think that pretty much covers it. I can go ahead and save this to you and send this to you along with the video. And hopefully that will help. If you have any questions, feel totally free to call me. I'll be more than happy to talk to you about it. Okay, good luck.